Hey there everyone, welcome back. This video will be an example of how to calculate the center of mass for a two-dimensional system. In this case, we have three discrete particles, but the same process will hold if it was a continuous or a solid object, right? So, as you saw in the last video, we're going to follow the same algorithm to calculate the center of mass in both the x and the y directions, right? And that algorithm is, I'll do it in the x direction first. The center of mass, right, the location or position is equal to, let's write it this way, 1 over the total mass, m tot, times the sum of the mass, so m sub I, times the position of that mass, x sub I. All right. So we have three masses here, or three discrete particles, each with their own mass. And so we'll have three terms from this summation. So let's see. And keep in mind that this effectively is an average, right? If you want to pause the video now and try and estimate and try and guess where the center of mass might be, right? Will it be closer to particle 2 up here, particle 1 down here, or particle 3 over here? And if you choose one, well, try and narrow down as much as possible, right? So, let's calculate it. All right, the total mass is, well, 1m plus 1m. Oh, I didn't mark it. Mass m. So 1m plus 1m plus 2m, that gives us a total mass of 4m. So 1 over 4 times m. Now times, let's see, mass 1 times position 1 plus mass 2 times position 2 plus mass 3, position 3. All right, now let's evaluate those. There we go. Okay. What I'm calling mass 1 is the one at the origin. So it has a mass of m, but an x coordinate of 0. Right? It has a location of 0, 0. So the x position, x1, is 0 in this case. And that term will effectively cancel. It will contribute to the center of mass in that it cancels. Okay. Mass 2, or I should say particle 2 up here, has an x coordinate of, well, whatever this is, right? This is an equilateral triangle of side length L, so that means that this bottom length here is L. Well, that means, here, I'll just write it in there. That means that this side length is L over 2, okay? And that is a right angle to the bottom. So particle 2 has a mass of m and an x coordinate of L over 2, okay? For particle 3, that has a mass of 2m and an x coordinate of, well, L. There we go. All right. So we have 1 over 4m times, let's see, we have, I'll tell you what, let me cancel out the m's, so that goes away, and then I'll cancel out all of the masses, right, or rather the variable m in all parts. So let me just go ahead and say that's 1 over 4. All right, and now we have L over 2 plus 2L. And so if we keep evaluating this, we have 1/4 times, let's see, 1/2 plus 2, 5/2 times L. And this will give us 5/8 times L, whatever that value is. So L over 2 is 4/8 L, right? This is 1/2. So that means purely in the x direction, 5/8, right? The center of mass of this system is somewhere along this line, right? Somewhere at that x position. So now let's find how high it is, right? The y coordinate. So the exact same algorithm, 1 over the total mass times the sum of all masses, mi, times their y position. In other words, y sub I. And so the total mass was 4m, so that doesn't change. And now, like before, up here we have the exact same thing, right? So I'm not going to write that in again. I'm a little bit more limited on space. But I hope you can see that the y-coordinate for masses 1 and 2 is 0. Right? This is y0, and those two are on that line. So m1, y1, and m3, y3 will be 0. So I will write that. What's the particle 2? What's the y-coordinate for particle 2? Right? What's that? Well, we have mass 2, which is just m, times something. Well, using the Pythagorean theorem, we can calculate that. So the hypotenuse, in this case, is L. So it's L squared minus the other side, which is L over 2, quantity squared. And that's all square rooted. So let's see here. We have, that's effectively L squared over 4, square root. And this is 4 over 4 minus 1. This is 3 over 4, L squared, square root. And that's L over 2, root 3. Let me check my notes real quick before I move on. Did I do that right? Yes. Okay. So L over 2 times root 3 is something. There we go. Squeeze that in there. So the masses cancel again, and we basically have L over 8 times root 3, right? And now we have that value, which is roughly 0.22 L. 0.22 times whatever the side length is. And by the way, 5/8 is roughly 0.63 L. Okay, so with those two, we can find the xy coordinate for the center of mass. So let's see, if that's 4/8, that's 6/8, that's 5/8. Okay, so 5/8 L, and then 0.22 is just under a quarter, right? So quarter L, I don't know, I'm going to estimate and say it's something like, so L might be up there, that's half, that's a quarter, go across, I'm going to say it's right there. So that is now the center of mass of the system. All right. So I hope you've enjoyed this video, right? It's a fairly straightforward application of, right, the center of mass algorithm. But if you think about it in terms of averages, right, that's what these terms effectively are averages. We can see that this 2m mass pulls the center of mass of the system towards it, right? If they were all equal, hopefully your intuition should tell you that the center of mass would be exactly in the center. But the center of mass is pulled towards the more massive object, right? And neither this mass nor this mass pulls the center of mass this way or that way. So what I can also draw is the bisector line along that direction. So we can see that the center of mass goes from there, it moves to right there, right? It does not go this way or that way. It simply moves closer to the more massive object, all right? All right, thanks for watching.